Hello there, and welcome to the Sleepy Space Channel. 4 centuries of travel end not with a landing, but with a decision, and the most likely version of that decision is to stay in orbit and never touch the planet at all. Stopping a Starship costs more than launching one, and the braking alone takes 30 years. The world the mission was named for was chosen from measurements 400 years out of date, and it may prove to be a dry rock with a breathable-looking atmosphere and no water anywhere on it. The people aboard have never flown in air, never stood in weather, and never carried their own full weight. Tonight we work through the whole arrival in order, from the first braking burn to the second century on the ground. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The half of the journey nobody plans for. Somewhere ahead of us, in a future we will not be present for, there is a ship that has been traveling for 400 years and has just begun to slow down. It is the largest object our species has ever moved. It has carried 15 generations of people who were born inside it and died inside it, and it is now approaching the star it was aimed at a speed that would cross the distance from here to the moon in under a minute. Everything about that ship has worked, and the hardest part of its mission has not started yet. This is the part of interstellar travel that gets left out of the story. We talk about the crossing, about the centuries of darkness and the sealed ecology, and the children born between stars. We rarely talk about what happens at the far end, because the far end is where the arithmetic turns unforgiving. A ship that reaches another star is not the same thing as a ship that arrives at one. Reaching is a matter of pointing correctly and waiting. Arriving means stopping, and stopping is the unsolved half of the problem. The reason is a piece of physics with no way around it. To gain speed, a ship must throw mass backwards. To lose that speed, it must throw the same amount of mass forwards. The two operations cost the same. There is no natural friction in interstellar space to help, no atmosphere to bleed the energy away, no ground to press against. Whatever velocity the ship built up over the first decades of its voyage, it must undo, entirely, using only what it still carries. And that requirement compounds in a way that is easy to state and difficult to accept. The propellant needed for the braking maneuver has to be carried from the beginning. It has to be accelerated along with everything else. So the ship must burn extra propellant at the start, simply to move the propellant it will need at the end. Work the arithmetic through, and the mass ratio for a mission that brakes is not twice the mass ratio for a mission that flies past. It is that ratio multiplied by itself. A factor of 10 becomes a factor of 100. A factor of 100 becomes a factor of 10,000. Missions that look merely difficult as a flyby become arithmetically absurd as an arrival. This is why almost every serious proposal for reaching another star quietly gives up on stopping. The best-known modern concept sends a sail weighing a few grams, pushed by an enormous laser array on the ground, up to something like 1/5 of the speed of light. It would cross 4 light-years in about 20 years, which sounds like a triumph until you follow it to the end. Moving that fast, the probe would traverse the entire destination system, from outer edge to outer edge, in a matter of hours. It would gather a few minutes of usable data as it went, transmit them back across 4 light-years, and continue outward into the dark forever. That is not an arrival. That is a photograph taken from the window of a passing train. For a probe, that may be worth doing. A few minutes of close-range data from another planetary system would be among the most valuable measurements ever made. But for a ship carrying people, the flyby is not a mission. It is a failure with a good view. So a crewed interstellar vehicle has to be designed around its braking system from the very first sketch, and that single requirement shapes everything else about it: its size, its structure, its propulsion, its schedule, and the entire arc of life aboard. Once you take that seriously, the shape of the journey changes. We tend to imagine the voyage as a long, level cruise with a brief maneuver at each end, the way a flight has a takeoff and a landing. The real profile looks nothing like that. Under most workable designs, the ship spends a decade or two accelerating, a few centuries coasting, and then between 2 and 5 decades slowing down. The deceleration is not a maneuver. It is an era. It is longer than most nations have existed in their current form. It is longer than the working life of everyone who begins it, which means there is a cohort aboard that lives its entire existence inside the braking phase. They are born into a world that is already slowing. They train, work, raise children, and grow old, operating a machine whose only purpose is to shed velocity. They will not see the ship stop. Their parents lived in a universe with no destination in any practical sense, because the destination was 14 generations away. Their grandchildren will live in a universe that has one. They live in the transition, and they are the only people aboard who know from birth that the journey ends and that they will not be there for it. There is a particular symmetry in that arrangement, and it is worth pausing on before we go any further. The people who launch a generation ship never see it arrive. The people who arrive never knew the people who launched it. And in between, there is a generation whose whole assignment is to slow something down that they will never see stop. Every part of this story has that shape. Nobody involved in a crossing of this kind gets to see both ends of their own work. The engineering consequences of a decades-long braking phase run deeper than they first appear. For centuries, the ship's main propulsion has been idle. Whatever plant produces its thrust, a fusion drive, a magnetic loop, a sail, or some combination, has been sitting unused across 15 generations, maintained by people who have never seen it operate. When the braking sequence begins, that machinery is asked to run at full output, continuously, for decades, hundreds of years after it was manufactured, with no possibility of replacement and no supply chain behind it. Every seal, every bearing, every superconducting joint is being asked to do the one thing it was built for, at the end of a working life longer than any machine we have ever made. And the ship changes character entirely. For most of its existence, it has been, functionally, a small sealed world in free fall, a habitat that happens to be moving. During the braking phase, it becomes a vehicle again. It has an orientation that matters. It has a direction of travel that can be felt. It has a schedule that everyone aboard is subject to, for the first time in 400 years, because the maneuver has to finish before the ship crosses the point where finishing is still possible. That deadline is the strangest feature of the whole sequence. A ship that fails to complete its deceleration does not crash into anything. There is nothing out there to crash into. It simply passes through the destination system, moving too fast to be captured by anything, and continues out the far side into interstellar space with its people still aboard and its systems still running. The star recedes. The planets recede. And the ship keeps going, carrying a population that watched their destination approach for decades and then watched it go past. There is no second attempt and no way to turn around, because turning around would cost exactly as much as stopping would have. So the arrival begins long before anyone sees the new star as anything but a bright point. It begins with a machine 4 centuries old, waking up to do the only job it was ever really built for, in front of an audience that will not live to see whether it worked. Everything that follows in this episode, the survey, the decision, the descent, the settlement, the century after, depends entirely on that one long maneuver finishing on time. Which raises the obvious question, and it is a genuinely difficult one. How do you stop something that heavy, moving that fast, with nothing to push against? Part 2. The 4 ways to slow a starship. There are, as far as anyone has been able to work out, only a handful of ways to remove speed from an interstellar vehicle. Each of them has been studied seriously. Each of them works in principle. None of them is comfortable, and the differences between them shape the entire arrival. The first and simplest is reverse thrust. The ship turns around at the midpoint of its voyage and burns its engines against its direction of travel for the second half of the trip. It is the most straightforward option and the most expensive one, because every unit of braking propellant had to be hauled along from the start. A ship built this way spends half its total existence pointing backwards, with its engines aimed at the star it is approaching and its living quarters trailing behind. For the second half of the journey, the destination is always behind the exhaust. The second method is magnetic braking, and it is one of the more elegant ideas in all of engineering. Interstellar space is not empty. It contains, on average, about 1 hydrogen atom in every cubic centimeter, and most of those atoms are ionized, which means they carry an electric charge. Charged particles can be deflected by a magnetic field. So a ship can carry a loop of superconducting cable, kilometers across in modest designs, more than 100 kilometers across in ambitious ones, run a current through it, and generate a magnetic bubble far larger than the ship itself. That bubble is not solid. It cannot be seen or touched. But every charged particle that enters it gets deflected, and every deflection transfers a tiny quantity of momentum from the ship to the particle. One atom does nothing at all. But a magnetic field 100 kilometers wide, sweeping forward at several % of the speed of light, intercepts an enormous number of atoms every second, and the accumulated effect becomes a real, usable drag. The ship is not pushing against anything material. It is pushing against the thinness of space itself, and finding that even the thinness has something to push on. The magnetic sail has one feature that matters more than any other. Its braking force depends on how fast the ship is moving. At high speed, the drag is strong. As the ship slows, the drag falls away. This is exactly the wrong shape for a smooth, controlled stop, because the method loses its authority precisely when the remaining speed becomes most stubborn. But it is a very good shape for the first and worst part of the job. A magnetic sail can take an enormous bite out of the top end of a ship's velocity and then hand the problem to something else. That something else is the third method, the electric sail, and it is the magnetic sail's mirror image. Instead of a magnetic loop, the ship deploys a grid of long, thin tethers and charges them electrically. Protons streaming past are repelled by the electric field rather than curved by a magnetic one. The physics is different enough that the performance curve is inverted. An electric sail is weak at very high speed and comparatively strong at low speed, which is where the magnetic sail has nothing left to give. Put the two together, and the arrangement makes obvious sense. Deploy the magnetic sail first, at the highest velocities, and let it strip away the top of the speed range over a couple of decades. Then switch to the electric sail for the long tail. Studies of exactly this combination suggest a ship can be brought down from about 5% of the speed of light to ordinary interplanetary velocities in something like 29 years, using both against roughly 40 years for magnetic braking alone and 35 for electric braking alone. Those numbers are estimates built on optimistic assumptions, but the shape of the result is robust. Two imperfect methods used in sequence beat either one used alone, and the whole procedure still takes 3 decades. The fourth method uses the destination star itself. A large, extremely light sail approaching a star can turn its reflective surface toward that star and let the pressure of starlight push against its incoming motion. Light carries momentum, and a sail is a way of collecting it. The force is small and it only exists close in, where the light is concentrated, so this is a method for the very last stage of an approach rather than the first. But there is a refinement that makes it far more powerful than it sounds, and it depends on the fact that the nearest star system to us happens to be 3 stars rather than 1. A sail can thread that system in a particular sequence. It arrives at the bright primary star, turns its face into the light, and is slowed and bent by a combination of radiation pressure and gravity. That bending sends it toward the second star, where the maneuver is repeated. Each pass sheds more speed and redirects the trajectory more sharply. If the geometry is threaded correctly, the sail can be handed down through the system and finally captured into a bound orbit around the faint third star, arriving not as a visitor, but as a permanent resident. The technique is sometimes described as using light and gravity together, each doing the part of the work the other cannot. The catch is a speed limit, and it is a strict one. To be captured rather than merely deflected, an incoming sail has to arrive below a specific velocity, and that velocity depends on how light the sail is for its surface area. For the most optimistic materials anyone has proposed, sheets a single atomic layer thick, the maximum injection speed works out to somewhere around 13,800 kilometers per second. That is about 4.5% of the speed of light, and it means a crossing time from here of roughly 95 years rather than 20. This produces the central irony of interstellar travel, and it is worth stating plainly because it governs everything. The faster you travel, the less able you are to stop. Speed and arrival are in direct competition. The fastest crossings anyone has designed are precisely the ones that cannot end in an arrival, and the crossings slow enough to be survivable at the far end take 4 or 5 times as long. There is no configuration in which a ship goes quickly and also stays. There is a fifth option, though it belongs to the very end of the sequence rather than the beginning. Once a ship is already inside the destination system and moving at something like planetary speeds, it can use the same techniques any spacecraft uses at home. It can steal velocity from the gravity of large planets by passing behind them. It can, in the most aggressive proposals, dip into the upper atmosphere of a gas giant and let the friction take the last of the excess. These maneuvers are familiar. Every probe we have sent to the outer planets has used the gravitational version. They are also, by this stage, dealing with a residual speed that has already been reduced by a factor of many thousands, which is why they belong at the end and nowhere else. Line all of this up, and the picture becomes clear. There is no single system that stops a starship. There is a chain of them, each covering a portion of the velocity range, each handing off to the next, each with its own hardware that must survive 4 centuries in storage and then work correctly on first use. And every one of those handovers is a point at which the sequence can fail, not dramatically, but by simply not shedding quite enough speed, leaving the ship traveling too fast to be held by anything in the system it came to. The braking chain also explains something about how such a ship would be shaped. A vehicle designed for magnetic braking is mostly loop. The habitat, for all its size, is a small, dense object at the center of a magnetic structure hundreds of times wider, and the loop is deployed once, at the start of the braking phase, after centuries folded away. A vehicle designed for photon braking is mostly sail, and the sail is so thin that its entire structure would tear under any load a person could apply by hand. In both cases, the part of the ship that people live in is a minor component, attached to something enormous and fragile, whose only purpose is to make the last few decades of the journey end rather than continue. Part 3. The decades, when the floor moves. Consider what the braking phase is actually like from inside, because it is one of the few parts of this story where the physics produces an experience rather than a number. A rotating habitat makes its own weight. The structure turns, and everything inside it is pressed outward, away from the axis of rotation. That outward press is what the people aboard call down. It has been down for 400 years. It is the only down anyone has ever known, and it points in a fixed direction relative to the walls, which is why the walls are where they are. A ship under sustained thrust makes a second kind of weight, and it points somewhere else entirely. When an engine fires, everything inside the ship is pressed toward the back, along the line of thrust. On a spacecraft with no spin, that thrust weight is the only weight there is, and it points along the ship's long axis. On a spinning ship, it does not replace the existing weight. It adds to it. Two accelerations pointing in different directions do not take turns. They combine. The result is a single effective weight that points somewhere between them, at an angle that depends on how hard the engines are pushing. And so, on the day the braking sequence begins, the floor of every deck in the ship tilts. Not visibly, not by much at first, but measurably and permanently. Water sits at an angle in a basin. A dropped object lands slightly off from where it was released. A corridor that has been level for 15 generations becomes very slightly uphill in one direction and downhill in the other. If the braking thrust is gentle, that tilt is small, and the ship simply lives with it. Floors are reshimmed. Drains are recut. Furniture is adjusted. It becomes one of the ordinary conditions of life during the deceleration, the same way a slight list becomes ordinary aboard a ship at sea. Children born during the burn grow up on floors that are subtly out of true and never think about it, and when the burn eventually ends, the floors will go level again, and that will feel wrong to them. If the braking thrust is strong, the ship has to be built to reconfigure. Designs that anticipate this problem mount the habitat sections on gimbals so the living decks can be swung to face the new combined direction of weight. In that case, the whole interior of the ship rotates within its own hull over the course of a few days, and everything not bolted down has to be secured, moved and remounted before it happens. That is a procedure with no precedent aboard, executed once, by people whose entire technical culture is built around never changing anything. And in the most extreme designs, the spin is simply stopped. If the braking thrust is strong enough to provide adequate weight on its own, there is no reason to keep rotating, and every reason not to, since the two effects fight each other. So the ship spins down. Over some hours, the familiar outward press fades, and a new press appears along a completely different axis. What used to be the floor becomes a wall. What used to be a wall becomes the floor. The entire interior geometry of the only world anyone has ever lived in is turned through a right angle and stays that way for 30 years. That reorientation is the single largest physical change in the ship's history, and it happens in the middle of the deceleration, rather than at either end of the voyage. It is worth holding on to as an image. The ship does not arrive and then change. It changes first, decades out, while the destination is still nothing but a bright point, and the people who perform the change do it on the authority of instructions written 400 years earlier by engineers whose names have long since become archive entries. The braking phase is also the first time in centuries that the ship makes noise. A coasting habitat is quiet in the deep sense. Its machinery is small, distributed and steady, and the background hum has been constant for generations. A ship under continuous thrust vibrates. Structural members carry load they have never carried. Something is always working, at the far end of the vehicle, and everyone can feel it, all the time, for decades. The people aboard would have no word for silence that means what our word means, but they would learn a new one during the burn. Then there is heat. Slowing a ship means converting an immense quantity of kinetic energy into some other form, and whatever else that energy becomes, a great deal of it becomes heat inside the vehicle. Heat in space has only one way out, which is radiation. There is nothing to conduct into, and nothing to convect through. So the ship must deploy radiator surfaces, large, thin, fragile panels held at high temperature, with an area comparable to the habitat itself, and those radiators must survive the entire braking phase without puncture. They are the least glamorous component in the whole architecture, and among the most likely to fail. The braking hardware itself is being eroded while it works. A magnetic loop sweeping through the interstellar medium at several percent of the speed of light is being struck continuously by the same particles it is deflecting, and some of those particles do not deflect. They arrive. Over decades, this sputters material off the structure, atom by atom, which is a slow process that becomes significant when it runs for 30 years without pause. The braking system is consuming itself while doing its job, and the calculation of whether it lasts long enough was made centuries ago. Meanwhile, the sky changes for the first time in living memory. For most of the crossing, the view outside a generation ship is essentially static. The stars are so far away that centuries of travel move them almost imperceptibly, and one of the defining conditions of the voyage is that nothing outside ever appears to happen. During the deceleration that stops being true, the destination star brightens steadily. Its companions separate from one another and become distinct points rather than a single one. The pattern of the sky ahead begins to open, slowly, over years, the first external change anyone aboard has ever witnessed. That is a profound shift in the psychology of the ship, and it does not need to be dramatized to be felt. A population that has never seen the outside world change anything is now living through a sky that is measurably different from year to year. Every child born during the deceleration grows up with the expectation that the stars move. Every elder remembers when they did not. And with the change comes something the ship has never had, which is a schedule. For 400 years there were no deadlines. Maintenance had cycles, agriculture had seasons, and people had lifetimes, but nothing outside the ship imposed a date on anything. The braking phase imposes one absolutely. The maneuver has to be complete before the ship crosses the point at which capture is still possible, and that point is fixed by the mathematics of the approach, not by anyone's preference. For the first time, a society organized entirely around continuity has to work to an external deadline that cannot be renegotiated, extended, or voted on. There is a quiet clash in that, and it is one of the more interesting features of the arrival. The ship's culture is a maintenance culture, tuned across 15 generations to avoid abrupt change and to distrust anything irreversible. The braking phase is nothing but abrupt change and irreversible commitment. It asks a conservative institution, quite abruptly, to do the opposite of everything it has learned to be good at, and it gives that institution about 30 years to learn how. By the end of it, If everything has worked, the ship is moving at something like the speed of an ordinary planet in its orbit. The star ahead is no longer a point, but a small disk with a visible edge. The engines fall silent, or the loop is furled, or the sail is turned edge-on for the last time. And the ship, for the first time in 4 centuries, is somewhere rather than merely between places. Part 4. When the destination stops being data. Everything the ship knows about its destination when it leaves is inference. That is not a criticism of the people who chose the target. It is simply the condition of astronomy across interstellar distance, and it holds no matter how good the instruments are. Consider what the 2 main detection methods actually tell us. A planet found by the wobble it induces in its star gives 2 numbers, an orbital period and a minimum mass. Minimum, because the size of the wobble we measure depends on the angle at which we happen to be viewing the orbit, and that angle is usually unknown. The planet could be exactly the mass we calculate. It could be twice that, or 5 times that, if the orbit is tilted the wrong way relative to our line of sight. A planet found by the shadow it casts as it crosses its star gives a different pair, an orbital period and a radius. Nothing about mass. Nothing about composition. Just how much of the star it blocks. Find the same planet by both methods and you get a mass and a radius together, which gives a density. That is genuinely valuable, and it is also less decisive than it sounds. A given density can be produced by a rocky world with a modest atmosphere, or by a smaller rocky world under a deep ocean, or by an even smaller core wrapped in an enormous envelope of hydrogen. All 3 fit the same number. The measurement narrows the possibilities without choosing between them. Then there are spectra. When a planet passes in front of its star, a thin sliver of starlight filters through the planet's atmosphere on the way to us, and the molecules in that atmosphere absorb at particular wavelengths. In principle, this reveals composition. In practice, across 4 light-years, it reveals the presence of 1 or 2 molecules at low confidence, and the interpretation depends heavily on assumptions about clouds and hazes that cannot be tested from here. A high-altitude haze layer flattens the entire signal and can make a rich atmosphere look like no atmosphere at all. So the ship departs toward a world it knows the way a person knows a stranger from a single indistinct photograph and a description read aloud by someone who has also never met them. And then it spends 4 centuries in transit, during which that photograph does not improve. The people who set the course are working from the best information the origin civilization could produce. The people who arrive are working from exactly the same information, 400 years stale, having had no way to add to it. What changes on approach is not gradual. It arrives as a series of thresholds, and each one converts a whole category of assumption into a category of fact. The first is parallax. For the entire crossing, the target stars have been shifting slowly against the background, the way a nearby object shifts against a distant landscape when you move your head. In the final stretch, the geometry becomes overwhelming. A system that was a single point for the whole voyage separates into individual stars with measurable separations. Their mutual orbits, previously derived from decades of careful observation from home, become directly visible. The architecture of the system stops being a model and becomes a picture. The second threshold is when the planets resolve. At sufficient closeness, an ordinary survey telescope, nothing exotic, just good optics carried as standard equipment, can separate the faint light of a planet from the overwhelming light of its star. This is the point at which the destination becomes an object rather than a signal. Phase curves become available, which means the ship can watch the planet's lit fraction grow and shrink as it goes around. The planet shows a crescent. The third is rotation. Surface features, cloud patterns, or simply variations in brightness as different regions turn into view, all betray how fast the world spins. This single number reorganizes everything else. A planet that turns on its axis in a day or two has weather that circulates, temperature that averages out, and a night that ends. A planet locked so that one face permanently confronts its star has none of those things and is a fundamentally different place. The fourth is atmosphere, properly this time. Instead of a marginal detection of one molecule, the ship gets high-resolution spectra across many wavelengths, repeatedly, through a complete orbit, from a distance of light minutes rather than light years. Surface pressure, composition, temperature structure and weather all come into focus over a few years of observation. This is the measurement the entire mission depends on, and it is the one that could not be made until the ship was nearly there. And the fifth threshold is the one nobody plans for, which is the system inventory. Moons, minor planets, asteroid populations, comet reservoirs, dust. None of it detectable from 4 light-years away, all of it appearing at once as the ship's instruments sweep the system for the first time. This is very often the most consequential category of discovery, because the resources that determine whether a settlement survives are rarely found on the headline planet. Water is more likely to be accessible on an icy moon than on a temperate world. Metal is more likely to be accessible in an asteroid than under a planetary crust and a gravity well. Now the uncomfortable part, and it is worth stating calmly, because the ship's population would have to hold it calmly too. The survey can go the other way. A world advertised as temperate can resolve into something with a surface pressure of 100 atmospheres, or 1/100th of one. A world with the right average temperature can turn out to have lost every molecule of its atmosphere to several billion years of stellar activity, leaving nothing but warm rock. An orbit that looked stable in the models can prove, on closer inspection, to be slowly changing under the influence of a large planet nobody knew was there. None of that would arrive as a single announcement. It would arrive as a slow accumulation of measurements over a decade, each one narrowing the range of possibilities, most of them ambiguous on their own. The realization that the destination is not what was expected would form gradually in a population that had been told a particular story about where they were going since childhood, and it would be several years between the first troubling number and any conclusion worth acting on. But the survey can also go the other way in the opposite sense, and this deserves equal weight. It can find more than was promised. A large moon around a giant planet with a thick atmosphere and accessible ice. A second rocky world further out that was simply too small and too cold to detect from home. A belt of asteroids so rich in volatiles and metals that building in orbit becomes obviously better than landing anywhere. The approach does not only threaten the plan. It routinely expands it, because 4 light-years of distance hides far more than it reveals, and everything hidden is discovered at once. There is a moment somewhere in all of this that would be remembered afterwards, and it is not a discovery in the dramatic sense. It is the first image in which the destination planet is more than 1 pixel across. The ship has known that planet was there for 400 years. Its existence is not news. But it is the first time anyone alive has looked at a world they did not build, resolved, with a shape and an edge, and a lit side and a dark one. Everyone aboard has spent their whole life inside a structure made by people. That image is the first thing any of them has ever seen that was made by nothing at all. Part 5. Reading the world from close range. Assume the braking has worked, and the ship has settled into the outer part of its new system, moving at ordinary orbital speeds. The planet it came for is now under continuous observation from a few light minutes away, rather than 4 light years. This is where the mission's founding premise is either confirmed or quietly taken apart, and it happens across a decade of patient measurement, rather than in a single afternoon. The properties that decide everything come down to a short list, and each one can be examined in turn. Surface pressure comes first, and it is the hardest thing to constrain from a distance. A world with a comfortable temperature and 1/100th of an atmosphere at the surface is a vacuum world in every way that matters. A person standing on it unprotected would lose consciousness in seconds, and their blood would begin to boil at body temperature. A world with a comfortable temperature and 90 atmospheres is a pressure vessel, where the air itself is dense enough to be treated as a fluid, and where every structure has to be built to resist crushing rather than to hold pressure in. The band in which an unprotected human being can simply stand and breathe is narrow, and nothing observed from 4 light-years away could have placed the planet inside it with any confidence. Composition comes next, and it is more demanding than the simple presence of oxygen suggests. Oxygen has to be present at the right partial pressure. Too little and a person cannot think clearly, let alone work. Too much and the fire risk becomes extreme, because everything flammable becomes far more so, and a settlement made largely of stored organic material would be living inside a hazard. Carbon dioxide is a stricter constraint still. It becomes physiologically significant at around 1% of a standard atmosphere, and dangerous well before it becomes any meaningful fraction of the air, which means a world could have an atmosphere that is almost entirely nitrogen and oxygen and still be unbreathable because of a trace component. Volcanic sulfur compounds do the same thing at even lower concentrations. Then, rotation. Around a small, cool star, the habitable zone lies extremely close in, close enough that tidal forces have had billions of years to slow the planet's spin until one face permanently confronts the star. That is the expected condition for most temperate worlds around the most common kind of star in the galaxy, which means it is the most likely thing the ship finds. A locked world has a day side where the star never sets, and a night side where it never rises. And whether such a place is habitable at all depends entirely on whether the atmosphere is thick enough to carry heat around from one to the other. A thick atmosphere can do it, and produce a world with moderate temperatures over much of its surface. A thin one cannot, and on such a world the night side gets cold enough for the atmosphere itself to freeze out onto the ground, which then drains the day side of air as well. Stellar activity is the 4th constraint, and small stars are far more active than our own for far longer. Their magnetic fields are violent, and their flares, measured against their quiet output, are relatively enormous. A single large flare from a small red star can briefly outshine the star's normal ultraviolet output by a very large factor and deliver a burst of charged particles to any planet close enough to be in the habitable zone. Over billions of years, that repeated erosion can strip a close-in world of its atmosphere entirely. So the ship might arrive at a planet in exactly the right orbit, at exactly the right temperature, and find bare rock. The 5th is the magnetic field, which is the planet's own defense against that erosion. A world with a strong internal dynamo deflects charged particles and holds its air far longer. Whether a tidally locked world can sustain such a dynamo is genuinely unresolved. Slow rotation weakens the effect, but the internal composition and the rate at which heat escapes the core matter more than the spin rate alone, and there is no way to measure any of that from orbit directly. It has to be inferred from radio emission and from the state of the atmosphere itself. Water is the 6th, and it deserves care, because the presence of water is not the presence of usable water. Ice locked at the poles of an otherwise airless world is water. Water bound chemically into the structure of minerals is water. An ocean under 100 kilometers of ice is water. None of those is a tap. What a settlement needs is water it can reach with the equipment it can land, in quantities that support agriculture, and the difference between a world with abundant water and a world with accessible water can be the difference between the mission working and the mission ending. And the seventh is gravity, which is the only one of these the settlers cannot adapt their equipment around. A planet of 1.5 times the Earth's mass, at a similar density, has a surface gravity roughly a fifth higher than ours. That is entirely survivable for a population raised in ordinary conditions. For a population raised in a rotating habitat tuned for comfort rather than for planetary readiness, arriving at a heavier world is a physiological problem that lasts for the rest of their lives. Two specific findings deserve their own place here, because they are the most likely disappointments, and also the most instructive. The first is what could be called the oxygen trap. Imagine a world close to an active star, absorbing a great deal of ultraviolet light. That radiation splits water molecules in the upper atmosphere into hydrogen and oxygen. Hydrogen is the lightest thing there is, and it escapes to space steadily. Oxygen is much heavier, and it does not. Run that process for 1 billion years, and you are left with an atmosphere containing a substantial fraction of oxygen, on a planet that has lost every drop of its water and has never hosted a single living thing. From 4 light years away, that world looks like the best news in the history of our species. An oxygen signature is exactly what everyone is searching for, because on our own world, oxygen is produced almost entirely by life. From close range, the same world is a desert with a breathable-looking atmosphere, no water, no soil, and nothing that ever lived. It is the one result that would justify the entire journey and then withdraw the justification on arrival, and it is not a remote possibility. It is a well-understood mechanism that we expect to be common. The second is the Terminator strip, and it is the more hopeful of the two. On a tidally locked world with a modest atmosphere, the day side may be too hot to work in, and the night side too cold to survive, but between them lies a permanent band of twilight. It is a ring around the entire planet, thousands of kilometers long and perhaps a few hundred wide, where the star sits forever on the horizon and never moves from it. In that band, the temperature can be moderate, water can exist as a liquid, and a settlement is genuinely possible. Everything about that landscape is stationary. The light is fixed. The shadows point the same direction permanently, and they never lengthen or shorten. The wind blows steadily from the hot side toward the cold side, driven by a temperature difference that never varies, so the weather has a prevailing direction that is written into the geography rather than the season. There is no morning. There is no evening. There is only a long, level, unchanging light lying along the ground, and a settlement built somewhere in it, in a place where the sun has been in exactly the same position for 4 billion years. And here, the strangeness turns around and points back at us. A population that has lived under manufactured lighting cycles for 15 generations, in a structure with no windows to a sky, arrives at a world where the star does not rise or set and never will. To us, that sounds like a deprivation. To them, it is simply a place with unusually good lighting. The sense that something is missing belongs entirely to the people who stayed behind, 400 years earlier, on a world that turned. Part 6. Navigating a system nobody has mapped. There is a quiet assumption behind every spacecraft we have ever flown, and it only becomes visible when it is taken away. Every probe we send across our own system navigates against a background of near-perfect knowledge. The positions of the planets are known to within meters. Their masses are known to many decimal places. The table of where everything will be at any given moment extends centuries forward and centuries back, and it is accurate enough that a spacecraft can be aimed at a point beside a moon it will not reach for 9 years and arrive within a few kilometers of where it intended. None of that exists at the destination. The ship arrives into a gravitational environment it must survey entirely from scratch, in real time, while still moving quickly, using only instruments it brought with it. The core difficulty is that orbits are only knowable through observation, and observation takes time. To establish the orbit of a small body, you have to watch it move against the background for long enough that its path curves measurably. To establish the mass of a planet, you have to watch something else respond to its pull. There are no shortcuts. A ship entering an unfamiliar system has months, perhaps a few years, of usable observation before it has to commit to a capture trajectory, and out of that, it must construct an entire working model of the system's mechanics. Every mass it has not yet measured becomes an error term in its own predicted path. In a system with more than one star, this becomes considerably harder. 2 stars in orbit around each other produce a gravitational field that changes with time in a way a single star does not. Stable orbits still exist, but they exist only within restricted zones, close enough to one star that it dominates, or far enough outside both that they act as a single mass. The boundaries of those zones depend on the mass ratio of the pair and on how elliptical their mutual orbit is, and they are not sharp lines but gradual transitions. A ship that parks near the edge of a stable region will find its orbit slowly changing over decades, and decades is exactly the timescale on which nobody notices immediately. The error would become visible long after the people who chose the orbit had died. The nearest system to our own, as it happens, is a triple. 2 stars broadly like our own in a long mutual orbit, and a small faint one at a great distance from both. Any ship aimed there is aimed at a moving arrangement of 3 masses whose configuration has advanced through many complete cycles during the 4 centuries of the crossing. The trajectory that was calculated at launch had to predict where all 3 would be on arrival, and the ship has to verify that prediction from the inside, with no outside confirmation available. Then there is dust, which is the hazard that scales worst of all. Interstellar dust is already a problem at cruise speed, where individual grains carry enough energy to punch through material. Dust inside a planetary system is denser by orders of magnitude, because it is continually resupplied by collisions among asteroids and by material shed from comets. The ship enters that region while still moving fast, and it enters it before it has any way of mapping where the concentrations are. This is one of the very few things about a destination that can be measured from home, and the measurement matters enormously. The dust in our own system is described in terms of a zodiacal cloud, and other systems are measured against it as a unit. Some systems have dust levels 100 times ours. Recent observations of the nearest Sun-like star have pushed the sensitivity down to only a few times our own level, which is the deepest such constraint achieved anywhere, and the result was reassuring. That system appears to be relatively clean. That is a meaningful piece of good fortune, and it is not guaranteed for any other target. A ship arriving into a system with 100 times our dust density would be flying through something closer to a sandblaster than to empty space. Dust also carries an implication beyond itself. Dust is produced by collisions, and collisions require a population of larger bodies colliding. A dusty system is a system with an active minor body population that no survey from 4 light-years away could possibly have inventoried. The dust is not just a hazard in its own right. It is evidence of everything else out there that has not been seen yet. And there is a category of object that stays invisible, no matter how carefully the ship looks. The outer reaches of any planetary system are expected to hold an enormous reservoir of icy bodies, left over from formation and orbiting so far out and so slowly that they reflect almost no light. In our own system, that reservoir is inferred entirely from the comets that occasionally fall inward from it. We have never seen a single one of the bodies still out there. The same would be true at the destination. The ship would arrive knowing, with confidence, that a large population of objects surrounds the system it has entered, and knowing nothing whatsoever about where any of them are. Those bodies are simultaneously the most valuable resource in the system, because they are made of the volatiles a closed ecology needs, and the least accessible thing in it. The radiation environment is the next unknown, and it can only be characterized on arrival. A quiet star produces a manageable particle flux. An active small star bathes its inner system in periodic bursts that briefly exceed its normal output by a very large factor. The shielding mass that was adequate for the interstellar cruise, where the main threat was cosmic rays arriving from all directions at a steady rate, may be entirely inadequate for parking close to a star that flares. And the ship cannot easily add shielding, because shielding is mass, and the ship has spent 400 years being exactly as massive as it is. Underlying all of it is a condition with no equivalent anywhere in our own experience of spaceflight. There is no outside check on any of this. No ground station running an independent trajectory solution. No second team to catch an arithmetic error. No rescue capability of any kind. If the ship's navigation model contains a mistake, the only entity in the universe capable of finding that mistake is the entity that made it, using the same assumptions that produced it. The prudent strategy is obvious and expensive. Park far out first, in the quiet outer reaches where the gravitational environment is simple and the dust is thin. Survey for 10 or 20 years. Build the model properly. Verify it against repeated observation. Identify every large body in the system, and only then move inward toward the planets. That approach is dramatically safer, and it costs propellant that a ship at the end of a 400-year voyage may simply not have. The safest plan and the affordable plan are not the same plan, and choosing between them is the first real decision the arrival generation makes. There is also a smaller problem that is oddly affecting. The ship has to rederive its own astronomical reference frame. All of navigation, at bottom, is done against the stars, and the pattern of the stars has shifted. 4 light-years of travel is enough to move the nearest stars noticeably and to redraw the familiar shapes entirely. The constellations recorded in the ship's archive, drawn by people on a world nobody aboard has seen, no longer match the sky outside. Somebody has to sit down and build a new catalogue, from scratch, defining a new set of reference points for a new location, and in doing so, quietly retires a set of patterns that human beings had been using continuously for tens of thousands of years. For all of that, the most likely navigational failure is not dramatic. It is not a collision, and it is not a missed capture. It is an insertion into an orbit that looked stable during the years it was studied, and turns out, over the following century, to be slowly decaying or slowly widening under the influence of a mass that was measured slightly wrong. The ship would have time to correct it, if it noticed. And noticing would require somebody, 3 generations later, to keep checking a number that everyone had agreed was settled long before they were born. Part 7. What happens when the planet is wrong? It is worth gathering up what we have so far, before going on. A ship arrives at another star only if it can stop, and stopping costs at least as much as leaving did. The braking is not a maneuver, but an era, 30 years or more, carried out by a generation who will not see it finish, on machinery that has been idle for 4 centuries. During that era, the floor of the ship tilts or turns over entirely. The sky changes for the first time in living memory, and a society built around continuity has to work to a deadline it cannot move. And when the ship finally slows, everything it thought it knew about the destination is replaced, threshold by threshold, with what is actually there, including a system full of moons and asteroids and dust that nobody could have seen from home. In a gravitational arrangement, the ship has to map from nothing. Which brings us to the outcome that most of this points toward, and it is not the one anybody imagines when they picture the end of such a journey. The most probable result of an interstellar arrival is that nobody lands. Not because of catastrophe and not because of failure, but because the planet turns out to be unusable and the alternatives turn out to be better. This deserves to be treated with dignity rather than as a disappointment, because it is where both the physics and the statistics point, and because the people it happens to would not necessarily experience it as a loss at all. Start with their actual situation. If the target world proves unusable, the arriving population is not stranded in any immediate sense. They are inside a fully functional closed habitat that has kept human beings alive continuously for 400 years, and they have just arrived somewhere full of raw material. In every material respect, their circumstances have improved enormously. The only thing that has failed is the stated reason for the journey. Consider what a planetary system offers a ship that has been sealed for 4 centuries. First, volatiles. Comets and icy bodies supply water, carbon, nitrogen, and oxygen, the 4 elements that a closed ecology consumes and slowly loses no matter how well it is engineered. Every airlock cycle vents a little atmosphere. Every chemical process locks a few atoms into forms nothing aboard can recover. Across centuries, those small losses accumulate into a real and irreversible depletion. Arriving at a system with ice in it is the first opportunity in the ship's entire history to put matter back in. Second, metals and silicates. Asteroids supply structural material, and structural material means the ship can grow. This is the single largest change in the population's material circumstances since launch, and it is difficult to overstate. For 400 years, the ship has been a fixed volume. Every square meter of floor was allocated centuries ago. Every expansion was impossible by definition, and the entire social structure, the population limits, the resource rationing, the careful management of who may have children and when, was built around a hard ceiling that could never move. On arrival, the ceiling moves. Third, energy. Around any star, a habitat has access to sunlight at intensities that interstellar space never offered. A ship that ran for centuries on whatever reactor it carried, husbanding its fuel, can switch to collection. Power stops being the constraint it has always been. Fourth, alternative destinations. A large moon of a giant planet may be a far better settlement target than the advertised world, often with accessible ice, lower gravity, no atmosphere to complicate the descent, and a magnetic environment that offers some shielding in the right orbits. A small rocky world further out, too cold and too dim to have been detected from home, may be exactly what a settlement needs, precisely because it is unremarkable. And fifth, the option of not landing anywhere at all. If the population can build habitats from asteroid material, the planet becomes optional. And here there is a serious argument that deserves to be stated plainly rather than treated as a consolation. A rotating habitat has controllable gravity. It can be spun to whatever weight its inhabitants prefer, and adjusted if they change their minds. It has a controllable day length, which can be set to whatever suits agriculture and sleep. It has no weather, no seismic activity, no seasons that anyone did not choose, and no biosphere that might object to being colonized. A planet has none of those advantages. A planet has a gravity that cannot be adjusted, a day length that cannot be tuned, weather that arrives without permission, and ground that occasionally moves. For a population that has spent 15 generations becoming very good at living inside a rotating habitat, the honest question is not whether they can settle a planet. It is why they would want to. The desire to stand on a world is an inheritance from ancestors who never asked them, formed on a planet none of them has seen, and it is entirely possible that it does not survive first contact with the alternative. Their grandparents' idea of a homecoming may look, to them, like being asked to move out of a house that works and into a field. There is a practical obstacle in front of that argument, and it is a large one. Building a second habitat would be the first genuine act of construction in the ship's history. Everything anyone aboard has ever done to their world has been maintenance, replacing a component with an identical component, repairing a seam, remachining a part to its original specification. Building something new, at scale, from material mined and refined on site, is a different discipline entirely, and it is one that the population has documentation for and no experience of. The first habitat they build would be built badly, by people learning the work as they did it, and it would probably take a generation. It helps enormously if the system contains a giant planet. A large world with a family of moons offers several things at once: abundant ice among those moons, a deep gravity well that can be used to change orbits cheaply, and, in the right places, a magnetic environment that provides some natural shielding from the star's particle output. The presence or absence of a giant planet in the destination system is one of the more consequential facts nobody could establish before arriving, and it may do more to determine where the settlement ends up than the habitable zone world that the mission was named after. This is also the point at which the mission's purpose can quietly change shape without anyone announcing it. A ship that cannot settle the planet can still settle the system. A ship that finds the whole system unsuitable can refuel from its comets, rebuild from its asteroids, and continue outward to another star, turning a mission with one destination into a mission with an indefinite number of them. That option requires an enormous manufacturing capability that no ship would launch with, which means the only way to reach it is to stay and build for a century first. Even the decision to leave begins with the decision to settle. There is one moment in all of this that would be remembered longer than any of the others, and it is a small one. Somewhere in the first years after arrival, a tender returns from the outer system, carrying a tank of water melted out of a comet, and that water is pumped into the ship's reservoirs. Until that moment, every atom aboard had been aboard since launch. Every molecule of water anyone had ever drunk had been drunk before, by people 4 centuries dead, and cleaned, and drunk again, through 15 generations of the same closed loop. That tank is the first new matter to enter the ship since it left. It is not a discovery, and it would not make anyone's list of the mission's achievements. But it is the moment the ship stops being a sealed system and starts being a place that trades with its surroundings, which is the actual definition of arriving somewhere. Part 8. The bodies that arrive. The people who arrive are not the same kind of people who left, and the difference is physical as well as cultural. A rotating habitat produces weight, but it produces it in a way that no human body evolved for, and 4 centuries of adaptation to that particular arrangement leaves marks that cannot be undone by deciding to be somewhere else. Begin with what is already known from short stays in weightlessness, because it establishes the direction of the effect, even though the magnitudes aboard a spinning ship would be much smaller. In sustained weightlessness, bone mineral density falls at roughly 1 to 1.5% every month in the parts of the skeleton that normally carry load. The losses are not evenly distributed. Over a 6-month stay, the lumbar spine and pelvis can drop by around 6% and the lower limbs by around 5%, while the skull actually gains slightly because fluid shifts upward when there is no weight to keep it down. The recovery figures are the part that matters most for an arrival. Returning to normal weight does not simply reverse the process. Bone rebuilds slowly, and the window in which formation outpaces resorption is limited. More than half of the people studied a full year after a long-duration flight had still not returned to the bone density they had before they left. The body treats reduced loading as new information about the world and adjusts accordingly, and it is reluctant to adjust back. A spinning habitat exists precisely to prevent this, and if the spin is generous enough, it largely succeeds. But spin gravity is not the same thing as gravity, and the differences are not subtle to the people living in it. It varies with height. The outward press is produced by rotation, so it falls to nothing at the axis and increases with distance from it. In a habitat of modest radius, a standing adult's head is measurably lighter than their feet, a difference of several percent, sometimes more than 10. Standing up quickly is a slightly different experience than it is here, because the weight distribution across the body changes as you rise. It has a sideways component. Anything that moves within a rotating structure is deflected, and the deflection depends on which direction the motion is in. A dropped object does not fall straight down, it curves as it falls, always in the same direction. A person climbing a ladder toward the axis feels pushed to one side, and a person descending feels pushed to the other. Throwing something across a room requires a correction that everyone aboard learns as a child and nobody thinks about. And it produces a sensation in the inner ear that has no counterpart here. Turning your head in a rotating environment stimulates the balance organs in a way that combines the head movement with the rotation of the whole structure, and the result is a brief tumbling sensation that depends on which way you turned. This effect is why habitat designers care so much about spin rate. A fast spin allows a small radius, but produces motion sickness in most people. A slow spin is comfortable, but demands enormous size. To produce a full standard weight at 2 turns per minute, a habitat needs a radius of about 200 meters, and at 1 turn per minute, it needs nearly 900. Almost certainly, a real generation ship would compromise. It would spin at a rate most people tolerate, at whatever radius the structure allowed, and accept a weight somewhat below the one their ancestors evolved under, because the alternative is a vehicle too large to build. Which means the population arriving at the destination has been raised for 15 generations at less than full weight. The consequences of that are predictable in direction, if not in size. Lower bone density throughout the load-bearing skeleton. Less muscle mass, particularly in the postural muscles of the back and legs, which are the ones a planet immediately demands. Reduced cardiovascular reserve and a blood volume tuned to a lighter environment. Reflexes for managing blood pressure while standing that have never been tested against a heavier one. None of these are illnesses. They are correct adaptations to the environment the body was raised in, and they become problems only at the moment that environment changes. There are other effects that are documented and less well understood. Immune function shifts in confined, low-diversity, low-gravity environments, with reduced responsiveness in some respects and increased reactivation of dormant viruses in others. Long-duration fluid shifts produce structural changes at the back of the eye that do not fully reverse. And the cumulative radiation exposure of a 400-year voyage, even behind good shielding, would produce effects on the vasculature and the nervous system that are difficult to characterize and would be worst in the oldest members of the arrival generation. And there is a medical constraint sitting underneath all of it that rarely gets mentioned. Medicines have shelf lives. Almost nothing in a pharmacy remains effective for more than a few years, and a great deal of it degrades into compounds that are simply inert. A ship on a 400-year voyage cannot carry its medicine. It has to manufacture it, continuously, from feedstock chemicals that must themselves be maintained and resupplied from the ship's own synthesis chain. Which means the medical capability available at arrival is not the capability that was loaded at launch. It is whatever the ship has managed to keep making, unbroken, for 15 generations. And the first landing is precisely the moment when that capability is most needed. Put it all together, and the picture is specific rather than tragic. The first person to step onto the destination world may need assistance to stand. Not because anything went wrong, and not because they are unwell, but because they are meeting, for the first time in the history of their family line, a weight that cannot be adjusted downward. Their heart has to learn to pump blood upward against a stronger pull. Their legs have to carry a load their legs have never carried. And their inner ear, calibrated since infancy to a world where every head movement produced a slight tumble, has to adapt to a world where head movements do nothing at all, which is itself disorienting, in the way that a sound you have always heard becomes noticeable by stopping. Weeks would fix most of it. Blood volume increases. Balance recalibrates. Muscle responds quickly to loading. Bone does not, and bone is the one that matters over a lifetime, because the arrival generation would carry skeletons built for a lighter world into a heavier one, and would be more prone to fracture for the rest of their lives. Their children, born on the surface, would have none of this. They would grow under full planetary weight from conception, and their bones would build accordingly. They would be taller or shorter, heavier or lighter than their parents, depending on the world, but they would be correctly built for it, in a way their parents never could be. And they would find it difficult to understand what the difficulty had been, in the way that children generally find their parents' limitations abstract. This produces the defining feature of the arrival generation, and it is worth naming clearly. They are a bridge in the most literal sense. They are physically adapted to a place they are leaving, and physically unsuited to the place they are going. Everyone who came before them belonged completely to the ship. Everyone who comes after belongs completely to the world. They are the only cohort in the entire history of the mission that belongs to neither, and their whole working life is spent making a transition that they will experience as difficulty and their grandchildren will experience as history. There is a last detail here that has a certain quiet weight to it. Any rational selection for the first descent would favor the young, because young skeletons have the most remaining capacity to adapt to a heavier world. The decision to land, however, would be made by those with standing and experience, which is to say, by the old. So the choice is made by people who will never set foot on the surface, and carried out by people who did not make it. That arrangement has appeared at every stage of this story, from the launch onward, and it appears one final time at the very end. Part 9. The skills nobody aboard has ever practiced. A generation ship is a maintenance culture, and that fact shapes everything about the people who arrive. For 400 years, every task anyone performs aboard is a repair, a substitution, an inspection, or an adjustment. Nothing is built at scale. Nothing is explored. Nothing is landed on. Nobody digs a foundation, surveys a valley, flies an aircraft, or manages a crop that is exposed to anything other than the conditions the ship has chosen for it. The entire skill inventory of the population is optimized for one thing, which is keeping an existing system from degrading, and that population is then asked, at the very end, to perform the most novel operation in its history. The gap is not in the archive. The archive is complete. Every procedure, every design, every textbook, and every recorded demonstration is available, catalogued, and preserved, because preserving things is what this culture is exceptionally good at. The gap is between recorded knowledge and practiced skill, and that gap is enormous and thoroughly understood in every field where anyone has tested it. A person who has read everything ever written about landing a vehicle has not landed a vehicle. A surgeon who has watched 1,000 recordings of an operation has not operated. The knowledge transfers. The competence does not. Work through what that means, item by item. Nobody aboard has ever flown in an atmosphere. Not once, in 15 generations. Nobody has felt turbulence or handled a vehicle whose control surfaces depend on moving air or experienced the way a wing behaves as it approaches a stall. Every pilot trained for the first descent is trained entirely in simulation, and the simulator is calibrated to an atmospheric model built from orbital measurements of a planet nobody has ever entered. The fidelity of that simulator is bounded by the accuracy of that model, which means the first crewed descent is, among other things, the first real test of the simulator that trained its crew. Nobody aboard has experienced weather. The concept exists in the archive as meteorology, thoroughly explained, with equations. The experience of standing outside while conditions change, without anyone having decided to change them, is entirely novel to every human being on the ship. In a shipboard environment, every variation in temperature, humidity, air movement, and light is the result of a decision made by someone. Weather is the first thing they will encounter that has no operator. Nobody has read a landscape. Judging whether ground is stable, recognizing a floodplain, seeing that a slope is a former landslide, noticing that a valley floor is where water collects, these are pattern recognition skills built up by walking over ground for years. They cannot be acquired from imagery. The first survey teams would be working in a landscape whose ordinary features they have no instinct for, on a world where the features may not follow familiar rules anyway. Nobody has built anything large. The ship was assembled in a system with industrial infrastructure, by an economy with mines and factories and supply chains. Building a settlement means excavation, foundations, pressure structures, life support and power distribution at a scale this population has only ever maintained. Their tool inventory reflects that. Individual precision instruments would be superb, lovingly maintained across centuries. Heavy equipment for moving Earth would either not exist or would exist as a single example, built from drawings, never used. And nobody has farmed outside a controlled loop. Shipboard agriculture is a managed system with known inputs, known light, known nutrients, and no surprises. Farming on a planet means soil chemistry that has to be measured, light that varies, temperatures that do what they do, and organisms, if the world has any, that are not in the manual. Even inside a pressurized greenhouse on the surface, the inputs come from an alien world and have to be characterized before they can be trusted. Then there is the lander itself, which is a harder problem than it first appears. A descent vehicle cannot simply be carried for 4 centuries and then used. Elastomeric seals perish. Propellants decompose or leak past their containment. Batteries degrade whether they are used or not. Pyrotechnic devices, which spacecraft rely on for separation events, have shelf lives measured in years rather than centuries. A lander stowed at launch would arrive as a museum piece that happened to be shaped like a spacecraft. So realistically, the lander is built during the voyage or after arrival, from stock the ship carries, or from material mined on site. It is built by people who have never built one, to a design that has never been flown, for an atmosphere that has only ever been measured remotely, using manufacturing processes reconstructed from documentation. Every one of those clauses adds risk, and they multiply rather than add, which produces a conclusion that is unglamorous and completely solid. The first descent is the highest risk single operation of the entire mission. Higher than the launch, which was performed by an industrial civilization with test programs behind it. Higher than the interstellar crossing, which was mostly waiting. Higher than the braking, which was long but gradual. The descent is a first flight of a new vehicle type, flown by an inexperienced crew into an unfamiliar atmosphere, with no rescue capability of any kind, and no possibility of a second vehicle if the first is lost. A rational mission would therefore stage it carefully. Send an uncrewed vehicle first and learn from it. Send a second uncrewed vehicle and confirm the lessons. Land equipment before people. Send a small crewed vehicle to a site already characterized from the ground. And accept, explicitly and in advance, that some of those attempts will fail, because that is what happens when a new vehicle meets a new atmosphere for the first time, and it happened repeatedly during our own first decades of spaceflight, with an entire planet's industry standing behind the effort. There is an image worth holding on to from this stage. The lander takes shape inside a bay that has held nothing but stores and spare stock for 400 years, a volume that generations of people walked past without ever having a reason to look into. Everyone who watches it come together is watching the first genuinely new large object their civilization has ever made. Their ancestors built ships, they have only ever repaired one. And the thing being assembled in front of them is not a replacement for anything, and has no precedent aboard, and exists for a purpose that nobody in the ship's entire history has ever had. Site selection carries its own quiet trap. From orbit, at the resolution available, a smooth plain and a field of boulders can look identical. Every landing our own species has attempted on another world has involved this problem, and it has been solved by sending orbiters first, mapping for years, and then still landing with hazard avoidance systems that scan the ground during the final descent. An arriving ship would have to do all of that from scratch, with instruments it built itself, on a world it has been observing for a decade rather than a century. There is also a slower kind of erosion in the archive that nobody would notice until it mattered. Procedures written 15 generations ago have been copied, reformatted, migrated between storage systems, translated as language drifted, and annotated by people who were interpreting rather than remembering. Every one of those steps is an opportunity for a small error, and small errors in procedures are invisible until the procedure is executed. The ship's documentation is not wrong in any way anyone can detect. It is simply 400 years removed from the last person who knew what it meant from experience. All of which is why the airless moon is such an attractive first target. Landing without an atmosphere is a harder problem in some ways. There is no free braking, so everything must be done on thrust. But it is a far simpler problem in the ways that matter here. There is no aerodynamics, no weather, no unknown density profile, and no heating. It is a problem of pure orbital mechanics, which is the one discipline this population has been practicing continuously, in the most demanding possible form, for the entire duration of their journey. Part 10. Biology meeting biology. If the destination world is dead, this becomes a chapter about contamination, running in one direction only. If it is alive, it becomes the most consequential encounter in the history of two separate biospheres, with the risk running both ways at once. Start with what the ship is carrying, because that part is knowable. A closed habitat's microbial community does not stay the way it began. It cannot. Over centuries in a sealed environment, with a limited pool of species and no resupply from a diverse outside world, microbial ecology simplifies and specializes. Some organisms disappear entirely because their niche never recurs. Others become far more dominant than they would ever be on a world with competition. And the selection pressures inside a spacecraft are unusual. They favor organisms that tolerate hard surfaces, survive disinfectants, resist desiccation, and shrug off radiation. We can already see the beginning of this on orbital stations, where the microbial community measurably shifts within months. Extend that across 400 years, and the result is not a copy of the biology that boarded. It is a descendant of a small sample of that biology, shaped for centuries by an environment that exists nowhere else in the universe. The ship's microbiome is, in a modest but real sense, native to the ship. That community is what would be introduced to a new world. And the introduction is permanent. There is no procedure anywhere in science that can unrelease an organism onto a planet. Once it is down and it survives, it is a permanent resident of that world, and the decision that put it there cannot be revisited by anyone, ever. Consider the two directions in turn. Forward contamination is the risk to the destination. If the world hosts native life, an introduced organism from the ship might find an empty niche and expand into it. Terrestrial microbes are extraordinarily versatile, and a great many of them make a living from chemistry rather than sunlight, in conditions that would kill anything larger. If even one of them takes hold, the science that the entire journey was undertaken to perform, the study of an independent origin of life, the only comparison our species could ever draw, is compromised in the first week. Our own space programs already take this seriously enough to sterilize landers, to restrict which regions of certain worlds may be visited at all, and to deliberately dispose of spacecraft in ways that keep them away from places where life might exist. Backward contamination is the risk to the settlers. If native life exists and can interact with human biology in any way, the settlement is exposed with no medical infrastructure beyond what it built for itself and no possibility of outside help. On our own world, we handle this with the strictest measures available. Material returned from a body that might host life is treated as hazardous until proven otherwise, and is handled under the highest level of biological containment that exists, the same standard applied to the most dangerous pathogens we know of. That is the level of caution applied to a few grams of rock returning to a planet with hospitals on it. A landing party has none of those advantages. Now the reassuring part, and it is more reassuring than most people expect. Life here is built on a specific handedness. Molecules can come in two mirror image forms, the way a left hand mirrors a right, and our biology uses only one form of its sugars and only the opposite form of its amino acids. There is no deep reason for that particular choice. As far as anyone can tell, it was settled early and arbitrarily, and everything since has inherited it. An independent origin of life on another world would have no reason at all to make the same selection. It might well make the opposite one. If it did, the consequences would be enormous and largely protective. Our enzymes would not recognize their molecules. Their enzymes would not recognize ours. A microorganism adapted to that world would find our cells to be an unfamiliar chemistry it has no tools to exploit, which is what an infection actually requires. Alien biology, in that case, would be largely non-infectious. It could not eat us, and we could not be its host. This is the most likely outcome, and it is quietly the most important fact in the whole scenario. It is not, however, safety. Chemical incompatibility rules out infection. It does not rule out harm. Fine biological particles cause immune reactions regardless of whether anything is alive or compatible. Allergy does not require a pathogen, only a protein the body objects to. Metabolic byproducts of alien organisms could be toxic on straightforward chemical grounds, in the way that many entirely terrestrial compounds are toxic to us, despite having nothing to do with infection. Spores and dusts damage lungs mechanically by being the wrong size and shape and sharpness. And an alien biosphere would fill its atmosphere with byproducts of its own metabolism, some of which might be perfectly harmless, and some of which might make the air unbreathable for reasons having nothing to do with oxygen. There is also a practical impossibility sitting at the center of all this. A robotic lander can be sterilized. It can be baked, chemically treated, assembled in a clean room, and delivered to another world, carrying essentially nothing. A crewed vehicle cannot be sterilized in any meaningful sense, because the crew is the contamination. A human being is not a passenger carrying microorganisms. A human being is an ecosystem, with more microbial cells in and on the body than there are human cells in it. The moment a person opens a hatch onto another world, that entire community is present, and no protocol can prevent it. This is why the choice to land is not a reversible experiment, but a permanent act, and why it belongs in a different category from anything a probe could do. The timing of the question is worth noticing too. Whether the destination world is alive may well be settled during the crossing rather than on arrival. An atmosphere held far out of chemical equilibrium, gases coexisting that should have reacted with each other long ago, is the clearest remote sign of a biosphere, and it becomes detectable as the ship's instruments improve with distance. So the debate over whether anyone may land could begin generations before there is anything to land on, and could be argued and settled and reopened repeatedly by people who will all be dead before it matters. The other case, the sterile world, is far safer and far less interesting. A dead planet offers no ecosystem services, no soil biology, no food, and nothing that can be harvested. It also offers nothing that can attack. Every gram of biology on such a world would be imported deliberately and would have to be established and defended indefinitely against a background of nothing. The settlement would be growing a small piece of one world inside pressurized structures on the surface of another, and it would be doing so alone. And this leads to an inversion worth sitting with, because it turns the entire dream of the mission around. Every version of this story that anyone tells involves finding a living world. That is the hope. That is the point, in most people's imagination, to cross the dark and find that something else is there. But a living world is the one outcome in which the settlers might not be permitted to land at all. Because a serious mission, thinking clearly, would recognize that an independently evolved biosphere is the rarest and most valuable thing their species will ever encounter, and that a human settlement on it destroys the very thing they crossed 4 light-years to find. The charter written 4 centuries earlier might say so explicitly. And even if it did not, the argument would be made, forcefully, by people who understood exactly what was at stake. So it is entirely possible that the best outcome of a 400-year journey is a population that arrives at a living world, studies it in detail from orbit for generations, learns more about biology than everything our species has ever known combined, and never once touches the surface. They would settle a moon instead, or build in orbit, and look down at the one place they wanted to go and agree, collectively and repeatedly, across centuries, not to go there. That is not a failure of the mission. It may be the most disciplined thing our species has ever done, performed by people nobody here will ever meet, for reasons that were written down before they were born. Part 11. The decision and the people who refuse it. 15 generations is long enough for a shipboard society to become a stable, settled, self-justifying system. Its governance was designed for one purpose, which is continuity, and it has been refined toward that purpose across 4 centuries by the simple mechanism of everything that threatened continuity being eliminated. Whatever the ship's political arrangements look like by the time it arrives, they are arrangements that have succeeded at avoiding large, irreversible changes for 400 years. And then the arrival asks for the largest irreversible change imaginable, from an institution built to prevent exactly that. The decision to land is not one decision. It is a cascade, and each step narrows what remains possible. The first is whether to survey carefully or commit early. A thorough survey means parking in the outer system and watching for 10 or 20 years before approaching anything. It is unambiguously safer. It also consumes propellant, life support margin, and, most dangerously, the political will to act at all. Institutions that spend 20 years studying a decision often discover that studying has become the decision. The second is which body to settle, if any. The advertised planet. A moon. An asteroid. An orbital habitat built from scratch. Or nothing, with the ship continuing as it always has, in a new place. Every one of those options has a constituency, and the arguments for each are strong enough that the disagreement is genuine rather than performative. The third is who descends first, and by what method they are chosen. Volunteers. A lottery. Selection by skill. Selection by physiology, since the young adapt better to a heavier world. Whatever method is used will be remembered for centuries, as a model of fairness, or as the founding injustice of everything that came after. There is no version of this choice that is not also a permanent political fact. The fourth is how much of the ship's irreplaceable capacity goes down the gravity well. Every machine landed is a machine no longer available to the people who stay. And a gravity well is not symmetrical. Getting something down is far easier than getting it back up. The equipment sent to the surface in the first decade is, for practical purposes, gone from the ship forever. The fifth is what becomes of the ship itself. Permanently crewed station, gradually stripped for material, or maintained indefinitely as the population's only guaranteed home. That decision cannot be unmade either, because a ship taken apart cannot be reassembled by a settlement that has not yet learned to build. Now the refusers, and they deserve real weight and no ridicule at all. To someone born aboard, the ship is not a vehicle. It is the world. It has geography, in the sense that it has districts with characters and histories. It has weather, in the sense that its systems have moods and seasons and known irregularities. It has continuity, in the sense that everyone they have ever loved lived and died within the same set of walls, and those walls are the only physical thing that has ever kept anyone alive. A planet, to that person, is an unbounded, uncontrolled, unpressurized expanse, where the temperature is decided by nothing and no one. There is no operator. There is no maintenance schedule. There is no way to check the readings and confirm that everything is nominal, because the readings are whatever a planet happens to be doing that century. The refusal to leave the ship is not superstition, and it is not cowardice. It is a reasonable preference for the only environment anyone has ever verified as survivable, held by people whose entire culture is built on distrusting untested systems. And this produces the arrival's quiet second act. The population splits. Some descend, some stay. Neither group is wrong, and both are viable. And within a few decades, the two are diverging in every measurable way. Different work, different daily physics, different risks, different bodies, and eventually different assumptions about what a normal life looks like. A ship that left one world as a single people becomes two societies at the other end, and the relationship between them is the real political history of the settlement's first century. There is a demographic consequence here, with hard numbers underneath it. If only part of the population lands, the surface settlement begins with a founder group smaller than the ship's total, and it inherits only the genetic and cultural variety of the people who went. Careful simulations of minimum crew sizes for multi-generational voyages put the lower bound at around 98 people under strictly managed breeding, enough to avoid immediate collapse from inbreeding, provided nothing goes wrong and the reproductive rules are followed exactly. If the goal is instead to preserve a representative sample of human genetic variation rather than merely to survive, the numbers rise into the thousands and in some analyses into the tens of thousands. A ship's population is already a bottleneck by those standards. A landing party drawn from that population is a second bottleneck stacked on the first. And the effective size, the number that actually matters for genetics, is always smaller than the head count, because not everyone has children, and those who do have different numbers of them. A settlement of a few hundred people is, genetically speaking, a settlement of rather fewer than a few hundred. The split halves something else too, and it is more urgent in the short term. Every specialized skill aboard exists in small numbers. Two people who can maintain a particular system becomes one aboard and one below. One person who understands a particular manufacturing process becomes either a ship asset or a surface asset, and whichever group does not get them loses that capability entirely. The redundancy that kept the ship alive for 4 centuries was built for a single population in a single place, and the moment the population divides, every one of those margins is halved. One thing the two groups would not lose is contact. At interplanetary distances, a signal takes minutes at most, so the ship and the surface can speak to each other continuously and share everything they learn. Their divergence would be cultural and physical rather than informational, which is a stranger arrangement than simple separation. They would know each other's news immediately and understand each other's lives less and less. Two populations can drift very far apart while remaining in constant conversation, and after a century of that, the conversation itself becomes the main thing they have in common. There is also a clock on the whole deliberation, and it is not a soft one. Life support systems have a remaining service life. Propellant reserves are finite and were sized for a maneuver, not for an extended period of orbital repositioning. Industrial stock, the raw feedstock a ship carries for making replacement parts, has been drawn down for 400 years and is now at whatever level 4 centuries of careful use has left it. Every year spent surveying and debating is a year subtracted from the margin available for acting. The decision cannot be postponed indefinitely, and everyone involved would know roughly how long they had, which is exactly the kind of pressure that produces either decisiveness or paralysis, and rarely anything in between. And whatever the first descent produces, the result would set the political legitimacy of the leadership for generations. A successful landing vindicates every decision that led to it, including the unpopular ones. A lost vehicle discredits the people who authorized it, permanently, and hands every subsequent argument to those who counseled waiting. The technical outcome and the political outcome are the same event, and there is no way to separate them. Underneath all of these decisions sits a question with no clean answer, and everyone involved would know it. The mission's charter was written by people 400 years dead, on a world nobody living has seen, for reasons that made sense in a civilization that no longer exists in any form. That document specifies what the ship is for. It may specify what must be done on arrival. And the people it instructs never agreed to any of it, were never consulted, and are separated from its authors by more time than most nations have existed. Whatever they decide, there would be a day when the last shuttle of the first descent wave departs, and for the first time in 400 years, the ship's population falls. The corridors are measurably quieter. And somewhere in the environmental systems, a controller that has been running the same balance since before anyone aboard was born senses fewer people and quietly reduces its output to match. Part 12. The first year on the ground. Suppose a landing happens and it succeeds. The first year afterwards is not a triumph. It is an audit, a systematic testing of every assumption made across 4 centuries, conducted under time pressure, with the ship overhead as the only backstop anyone has. Energy comes first, because a settlement's entire capability is bounded by how much power it can make. Around a small, cool star, the total light arriving at a world in the habitable zone is comparable to what our own world receives, since the habitable zone is defined by exactly that. But the light is distributed very differently across wavelengths. A small red star emits heavily in the red and the near-infrared, and comparatively little in the blue. Solar panels are not neutral instruments. Their efficiency depends on the spectrum falling on them, and a panel designed for one star's output loses a meaningful fraction of its performance under another's. Every array the settlement lands has to be matched to a spectrum that was only measured properly a decade before they arrived. Then food, which is harder. Crops brought down from the ship's growing bays are adapted to a specific artificial light recipe, a specific nutrient solution, a specific temperature, and a specific day length, refined across 15 generations of selection inside a closed system. Planting them under an alien star means giving them light that is the wrong color. Terrestrial photosynthesis is tuned to the wavelengths our own star produces most abundantly, and under a small red star, the number of photons available in that useful range is substantially lower. Estimates of productivity under such a star run well below terrestrial values at visible wavelengths, in some analyses several times lower. There is a partial answer, and it is interesting enough to be worth stating. Some organisms on our own world already extend their photosynthesis into the near-infrared, using pigments that absorb light well beyond the range most plants can use, out to wavelengths approaching 750 nanometers. These are not exotic laboratory constructs. They are ordinary cyanobacteria that adapted to shaded, filtered environments where only the long wavelengths reach. Under a red star, those organisms would have a substantial head start over everything else in the ship's biological inventory, and a settlement would very likely find itself building its food system around them rather than around the plants its ancestors ate. Day length is the other agricultural problem, and on a tidally locked world, it is not a problem so much as an absence. There is no day length. The light is constant, unchanging, and comes from a fixed direction forever. Some plants tolerate that well. Many do not, because flowering and fruiting in a great number of species are triggered by changing day length. The plant measures the shortening or lengthening of the light period and uses it as a calendar. On a world with no calendar in the sky, that trigger never arrives, and the plant simply grows and never reproduces. Every crop would need its own artificial light cycle imposed on top of the natural illumination, which means agriculture on the surface is no simpler than agriculture aboard the ship. Soil is the next surprise, and it is a conceptual one. A sterile world has ground, but it does not have soil. Soil is not crushed rock. Soil is a biological product. mineral particles bound together with organic matter, water, air spaces, and an enormous living community of bacteria and fungi that cycle nutrients, fix nitrogen, and make minerals available to roots. Manufacturing it means importing the biology, giving it organic matter to work with, and waiting years for it to establish, all inside a pressurized structure, because none of those organisms could survive outside. The ground may also be actively hostile. Regolith on worlds in our own system contains reactive salts that are toxic to most terrestrial life and would have to be identified, and then washed out with water the settlement can barely spare before anything could be grown in it. That washing produces contaminated water that has to be dealt with. Every solution in a settlement's first year generates its own second problem. Water itself follows the same pattern. Even on a world with abundant ice, the water must be located, reached, extracted, melted, purified and transported, and each of those steps needs power and equipment. Abundance is not access. A settlement sitting on a frozen ocean can still run short of water if the machinery for getting at it fails. Radiation shapes where people live. Without a thick atmosphere and something like an ozone layer, the ultraviolet flux reaching the surface can be severe enough to damage unprotected tissue quickly, and around an active star, the periodic particle events are worse still. The cheapest protection anywhere in space is mass, and the cheapest mass is the ground itself. A few meters of regolith piled over a structure reduces the dose enormously and costs nothing but excavation. So the first settlement is almost certainly buried, or built into a slope, or roofed with bagged soil. It would not look like the settlements in the archive's illustrations. It would look like earthworks. And then dust, which is the most reliably underestimated hazard in every landing scenario anyone has ever run. Fine particulate on a world with a thin atmosphere is sharp because there has been no water and no weather to round it off. It clings electrostatically to everything. It works into seals and bearings and destroys them. It scratches optics and visors. Inhaled, it damages lung tissue mechanically, regardless of chemistry. Every airlock cycle brings some of it inside, and over years, the accumulated quantity inside the habitat becomes a health problem in its own right. There is one feature of a tidally locked world that works in the settlement's favor, and it is worth crediting. Because the star never moves, the thermal situation never changes. Heat always flows the same direction, from the day side toward the night side, permanently. There is no night to design for, no seasonal swing, no dawn to survive. A structure built to handle the conditions at one moment is built to handle them at every moment thereafter, which removes an entire category of engineering margin. The wind blows the same way for the same reason, steadily, from the hot side toward the cold, which makes it something a settlement can plan around, rather than defend against. And the population would be too small at first to specialize. On the ship, generations of careful training produced people who did one job extremely well. A first settlement of a few hundred cannot afford that. Everyone does several jobs adequately, and none of them expertly, which is a sharp and demoralizing change for a culture built on deep competence, and it lasts until the settlement is large enough to let people concentrate again. The strategic reality behind all of this is that the settlement cannot be self-sufficient for a long time and would not sensibly try to be. It is an outpost, supplied from orbit, and it stays that way for decades. The ship is the hospital. The ship is the factory. The ship is the archive, and the refuge, and the guarantee. Independence is not a first-year objective. It is a second-century objective, and pretending otherwise is how outposts fail. The most useful way to put the whole first year is this. You cannot land a civilization. What lands is a set of tools that make tools, machines whose purpose is to produce the machines that will eventually produce the things people actually need. That chain of bootstrapping runs through metallurgy, chemistry, power generation, and precision manufacture, and each link has to be established before the next becomes possible. It is measured in decades, not seasons, and for most of that time, the settlement produces nothing anyone would call a product. Somewhere in the middle of that first year, there would be a birth on the surface. It would be a medical event with no precedent in the ship's records, a gestation carried out under a gravity nobody has gestated in a radiation environment that has never been tested, by a mother whose own body was built for a lighter world. That child is the first member of the species in 400 years to be born on a planet, and the first ever to be born on that one. Everything the settlement is doing is, in the end, for the sake of people like that, and none of the adults present would be able to tell, from looking at the infant, whether any of it had worked. Part 13. The message that may reach nobody. An arriving ship would send word home. It is the natural thing to do. It costs comparatively little, and it is the only remaining connection to the place the mission began. But the shape of that communication is worth working through carefully, because it is one of the stranger features of the entire scenario, and one of the least discussed. The signal travels at the speed of light, which means a report sent from 4 light-years away arrives 4 years and a few months after it leaves. A question asked from home and answered from the settlement takes more than 8 years to complete a single exchange. There is no conversation in any sense we would recognize. There is only alternating monologue, with each side addressing a version of the other that is years out of date, and every message crossing several others in flight. That much is simply arithmetic. The harder part is who receives it. The ship left 4 centuries ago. Whatever institution launched it, a nation, an agency, a coalition of nations, a company, some arrangement we do not have a word for yet, has almost certainly not survived in a recognizable form. 400 years is longer than the great majority of political entities in recorded history have lasted in continuous form. The organization that wrote the mission charter, funded the construction, selected the crew and set the course, is, from the perspective of the arrival, an entity from deep history. The practical consequences are ordinary and quite deflating. Receiving equipment has to be maintained, aimed and staffed. Frequencies have to remain allocated. Somebody has to know what the signal will look like and when it might come. 4 centuries is long enough for the receiving antennas to have been repurposed for other work, dismantled for materials, or simply left to weather. It is long enough for the mission to have passed out of active memory and into the category of historical curiosity, the sort of thing that is broadly known about and specifically forgotten, appearing in general histories and in nobody's operational plans. There is also a pointing problem, and it is genuinely difficult. Neither end of this link is stationary. Both stars are moving through the galaxy on their own paths. A settlement transmitting home must aim not at where its origin is, but at where its origin will be when the signal arrives, 4 years later, a calculation requiring accurate knowledge of a motion measured centuries ago from a different vantage point. There is a power problem underneath the pointing problem. Sending a detectable signal across 4 light-years requires either an enormous transmitter or an enormous receiving aperture, and preferably both. Signal strength falls with the square of distance, and 4 light-years is a very large number to square. The settlement, newly arrived and short of everything, would not have the industrial capacity to build a powerful transmitter for decades. What it can afford early is a beacon, A simple, narrow, repeating signal carrying very little information, which costs a small fraction of what a full data link would. So the first message home is likely to be short. Not a report. An announcement that something is there. And there is the matter of language. 15 generations is long enough for speech to drift substantially. Vocabulary shifts, pronunciation shifts, and the words for things that exist only aboard the ship multiply, while the words for things nobody has ever seen quietly fall out of use. There is no reason for a shipboard population to retain a working vocabulary for rain, or for coastline, or for crowd. The settlers may still write in the launch language, because writing is conservative and the archive preserves it, and speaks something noticeably different. Which means the message home might be composed in a formal language its authors do not use with each other, the way a person might write in a language they learned from books. Assume all of that is solved. There are still several ways the message can land. It may arrive at a civilization that has moved on technologically and is no longer listening in the relevant way with the relevant equipment. The signal arrives and simply falls on ground with no receiver on it. It may arrive at a civilization that has already sent a second, faster ship, one that departed a century after the first, traveled at 3 times the speed, and arrived decades earlier. In that case, the settlement's triumphant first report is news that its recipients have known for a generation. This is not a fanciful scenario. It is a direct consequence of technological progress, and it has a name in the literature of interstellar travel, the argument that it is always rational to wait, because any ship launched now will be overtaken by a better ship launched later. Taken seriously, that argument says nobody should ever leave, right up until the moment progress stalls, at which point it evaporates entirely. The trap only closes on those who are impatient during a period of improvement. It may arrive at nobody at all. 400 years is long enough for a civilization to end. And the settlers would have no way of establishing that, because silence is not evidence of anything in particular. To conclude that no one is there would require decades of listening across many frequencies, and even then the conclusion would be provisional. A silent origin might be extinct. It might be uninterested. It might be listening and choosing not to reply. These are indistinguishable at 4 light years, and they remain indistinguishable indefinitely. Or it may arrive perfectly, be received with enormous interest, and be answered warmly and in detail by people who are now, unavoidably, strangers. 4 centuries of separation, followed by an exchange in which every remark takes 8 years to complete a round trip, does not produce a relationship. It produces 2 archives corresponding with each other. The most valuable thing the settlers could send, incidentally, is not news of themselves. It is data. A complete close-range survey of another planetary system, its star or stars, its planets, its moons, its dust, its chemistry, its biology, if it has any, is a scientific return that would justify the entire cost of the mission to the origin civilization, regardless of whether anyone ever settled anything. That is the one deliverable the crossing guarantees. Everything else about the mission may fail, and the survey still arrives. What all of this produces is a relationship with no good analogy anywhere in human experience. It is not exile, because nobody was sent away in punishment, and nobody is prevented from returning by anything but physics. It is not emigration, because emigrants can write home and expect an answer within a life, and their descendants can visit. It is not independence, because no one declared anything, and no relationship was severed by any decision. It is simply separation, total, permanent, and produced entirely by distance, complete long before anybody thought to notice it had happened. So the settlers composed their message with enormous care, as anyone would. They would draft it and redraft it. They would argue about what to include and about what tone to take toward people they have never met. They would want to be worthy of it, and they would want it to be clear, and they would want it to say something about the 15 generations who lived and died on the way, none of whom the recipients ever knew existed as individuals. And then they would send it, into a silence that may or may not be listening, and go back to work, because the answer, if it comes at all, will arrive at a settlement run by their grandchildren, and there is nothing to be done in the meantime but continue. Part 14. The second century. The most revealing part of an arrival is not the landing. It is what the situation looks like 100 years afterwards, when the arrival generation is gone, and the outcome has settled into whatever it is going to be. 3 broad outcomes cover almost everything, and none of them deserves to be ranked above the others. In the first, the settlement takes. Agriculture stabilizes after decades of failures. Industry bootstraps, slowly, through the long chain from mining to metallurgy to precision manufacture. The population grows past the point where any single accident can end it. And within a century or two, there is a functioning society on the ground that no longer depends on the ship for anything essential. The ship by then is very old, 4 centuries at launch, 5 now, and becomes either a maintained orbital station or a source of material to be carefully dismantled, or an object left in a stable orbit that nobody visits and everybody can see. In the second, the settlement holds without growing. The outpost survives, permanently supported from orbit, never quite achieving independence. Its population stays small enough that specialized skills remain fragile, and every capability rests on a handful of people. This is a stable configuration and could persist indefinitely. It is not settlement in the sense anyone intended, and it is not failure either. It is a research station with families in it. In the third, the surface is abandoned, and the system is settled instead. The planet proves too costly, or too hostile, or simply not worth the effort compared with the alternative, and everyone returns to orbit, where habitats built from asteroid material offer better conditions than the world ever could. Adjustable weight. A chosen day length. No weather and no seismicity. In this outcome, our species establishes itself around a new star permanently, without ever standing on a world there, and after a few generations, nobody finds that strange. Across all 3, one process runs the same way, and it is the most certain thing in this entire episode. Divergence. 2 populations living under different gravity, different radiation, different light, and different daily risk will drift apart physically within a few generations. Bone density and stature respond to weight. Cardiovascular function responds to load. Immune systems respond to what they encounter. None of this requires anything as slow as evolution. It is ordinary development, the same process that makes a person raised at high altitude physiologically different from a person raised at sea level. Add centuries, and selection begins to work on top of that, and the drift becomes structural rather than merely developmental. And this points to the most honest reframing available for the whole endeavor, which is worth stating plainly. The point of a crossing like this was never to move humanity somewhere. Humanity does not move. What crosses is a sample, a few hundred or a few thousand people, carrying a fraction of the species' genetic variety and a fraction of its culture and the whole of its archive. What arrives at the far end, generations later, is not humanity relocated. It is a branch, related to us, informed by the same accumulated knowledge, and increasingly and irreversibly its own thing. Measured against the goal of moving our species to a new home, that looks like a shortfall. Measured against the goal of making sure there is more than one of us, it is exactly the intended result. A species confined to a single world has one point of failure and no redundancy of any kind. A species with a second, independent, self-sustaining population around a different star cannot be ended by any single event. That was the entire strategic argument for going, and the divergence is not a flaw in it. The divergence is the product. There is a threshold underneath all three outcomes that decides which one occurs, and it is a population number rather than a technology. Industrial capability requires specialization, and specialization requires enough people that individuals can spend their lives on one narrow thing. Below some minimum, a society cannot maintain the full chain from raw material to finished machine, and capabilities begin to drop out of it, not dramatically, but one at a time, as the last person who could do something dies without a successor. And a settlement that loses a capability cannot recover it from anywhere. There is no import. There is no neighboring town that still knows how. The knowledge sits in the archive, complete and unusable, waiting for a population large enough to relearn it. Which makes archive maintenance a civilizational priority in a way it has never been here. Everything our species knows is in that archive, and it is the settlement's only link to accumulated human knowledge. It has to be copied, migrated, verified and protected across centuries by people who understand only a fraction of what it contains, against the possibility that some future generation will need a technique nobody currently living can perform. And the founding story hardens. 100 years is long enough for the arrival to stop being a memory and become a narrative, the decisions of the arrival generation retold until they acquire the shape of either a legitimizing myth or a standing grievance. Whether the first descent was a triumph of nerve or an act of recklessness that killed people unnecessarily is a question that gets settled, eventually, not by evidence, but by which version the schools teach. Which brings all of this back here, to us, and to what such a project would actually look like from the inside. If a ship left now, nobody alive would learn anything. The crossing alone consumes centuries. The report of the arrival then takes years more to come back. The whole enterprise is structurally invisible to the people who fund it, build it, and launch it, the largest project a species could undertake, producing no feedback of any kind to the generation that undertakes it. There would be no confirmation, no return, no news. There would only be the launch, and then 400 years of not knowing, borne by people who never chose to bear it. That is the real difficulty at the center of this, and it is not a technical one. Every technical problem in this episode has at least a candidate solution. Braking has 4 or 5. Navigation has procedures. Contamination has protocols. Physiology has countermeasures, imperfect but real. What has no solution is the requirement that a civilization commit resources on a scale nothing has ever matched, sustain that commitment unbroken for longer than most civilizations have existed, and receive its reward in the form of a message to its distant descendants about a place it will never see. And yet the arrival is the only part of the story worth the trouble. The crossing is a physics problem, and physics problems, in the end, are only expensive. The arrival is where the thing either becomes a place or does not. Everything before it is transport. So let the last image be a simple one. There is a point of light that has been in our sky for the whole history of astronomy, catalogued, measured, photographed, argued over, and never once resolved into anything but a point. Every instrument we have ever built has looked at it and returned the same answer: too far, too small, a dot. And then, 400 years after a ship leaves, Somebody who has never seen our world, whose ancestors 12 generations back were the last to breathe air that was not recycled, sits at a window and watches weather move across the face of it. Cloud systems turning. A Terminator line that does not move. Ice at one edge catching the light. They would not find it remarkable in the way we would. It would be, to them, simply the view. And that is the strangest and gentlest part of the whole story, that the thing we would give anything to see would belong by then to people for whom it was ordinary. And so the ship settles into its orbit around a star that is not ours, carrying people who were never asked whether they wanted to go, above a world that will be a home or will not be. Whatever they decide slowly, and there is no hurry in any of it. The light will still be there in the morning, and the morning will come whether anyone is watching or not. Let your breathing slow. Let the day fade away. Sleep well and good night.